Quantum computers, they don't speak Python or Java. They have their own language, a language of pure potential, and it's written in something called quantum circuits. So in this explainer, we're going to dive into these incredible blueprints and figure out exactly how they tell some of the most powerful machines on Earth what to do.
So, how do you even program one of these things? It's the big question, right? It's not like you can just open a text editor and start typing code like you would for your laptop. No, the answer is in a special kind of diagram. Think of it like a master plan that lets us tap into all the weird, powerful rules of quantum mechanics and actually turn them into a computation. So here's our game plan. First, we'll define what this quantum blueprint actually is. Then, we'll break it down into its core parts, the wires and the gates. After that, we'll check out the essential single qubit toolkit before we use it to build an actual entangled state. And finally, we'll see how you can read the results. Okay, let's start with that big picture. What exactly is this quantum blueprint we keep talking about? At its absolute heart, a quantum circuit is just a model for computation. It's a visual map, really, a sequence of operations, which we call gates, that get applied to our quantum bits, or qubits. Think of it as a flowchart, but instead of simple yes-no logic, it's a flowchart for manipulating probability and potential. It's how we turn abstract quantum theory into a concrete set of instructions. All right, so let's break this blueprint down into its essential parts. Just like a classical circuit has wires and logic gates, a quantum circuit has its own unique components that let it work its magic. And this is where things get, well, quantum. A classical circuit is pretty straightforward, right? Your bits are either a 0 or a 1. Predictable. But qubits, they're playing a totally different game. They can be a 0, a 1, or, and this is the mind-bending part, both at the same time. That's superposition. So the whole logic shifts from being predictable to being probabilistic. You're not just calculating one single answer anymore. You're calculating the probability of every possible answer all at once. So every single quantum circuit you'll ever see is built from these three core pieces. The wires aren't physical wires, by the way. They represent the lifetime of a qubit as it travels through the computation. The gates, those are the actions, the operations we perform on those qubits. They're like the verbs in our quantum sentence. And finally, you've got measurement. This is absolutely crucial. It's the act of looking at the qubit, which forces it out of that fuzzy quantum state and into a classical 0 or 1 that we can actually read. Now that we know the basic parts, let's get our hands on some tools. We're going to start with the simplest ones, gates that only operate on a single qubit at a time. This is really our foundational toolkit. Okay, let's look at three of the big ones. First, the X gate. It's the simplest. It just flips a qubit from 0 to 1 or 1 to 0. It's basically the quantum version of a classical NOT gate. Then you've got the Z gate, which is a bit more subtle. It performs a phase flip. You can kind of think of it as leaving the probabilities of 0 and 1 the same, but changing their relationship to each other, which is super important when qubits start interacting. But the real star of the show here is the H gate, the Hadamard gate. This is our superposition creator. This is the one that takes a definite qubit and bam, puts it into that 50-50 state of being both 0 and 1 at the exact same time. Okay, we've got our blueprint. We've got our basic tools. Now for the main event. We are going to use these really simple components to create quantum entanglement, that spooky action at a distance that even Einstein was so fascinated by. So our goal here is to build what's known as a Bell state. It is the textbook most fundamental example of two entangled qubits, where the fate of one becomes instantly, and I mean instantly, linked to the fate of the other, no matter how far apart they are. All right, let's do this. Circuits are always read from left to right. So first thing, we start with our two qubits. We initialize them both in the simple 0 state. On our diagram, that's just two clean parallel wires. It's our blank canvas. Next up, the first bit of quantum magic. We take that Hadamard gate we just talked about, and we apply it to the top qubit. That single action instantly puts the qubit into a superposition. It is now in a 50-50 state of being both 0 and 1 simultaneously. And now for the final step, we link them. We use something called a CNOT, or controlled NOT gate. It connects the two qubits and it follows one very simple rule. If the top control qubit is a 1, it flips the bottom target qubit from 0 to 1. But if the top qubit is a 0, it does absolutely nothing. And just like that, with only two gates, we've created entanglement. Now you can ignore the math for a second. What this means is that these two qubits are now a single system. Because that first qubit was in a superposition of 0 and 1, they are now locked together. If you measure one and find out it's a 0, the other one will instantly be a 0, even if it's miles away. If one is a 1, the other's a 1. Their fates are completely intertwined. So, we've designed our blueprint, we've executed the instructions, but how do we actually see what we've made? How do you read the output of a circuit like this? Well, there are two main ways to see the output. The first is direct measurement. This act of observing forces the quantum system to pick a side, to collapse into a single classical state. So for our Bell state, we'd always get either 0, 0 or 1, 1, each with a 50% chance. The other way is to use simulators, and these things are amazing. Tools like these let you peek behind the curtain and see the probabilities of the whole system without forcing it to collapse, which is, as you can imagine, incredibly useful for designing and debugging your circuits. So, what's the big takeaway from all of this? Quantum circuits are so much more than just a bunch of diagrams. They are the essential language, the visual grammar that we use to build, to understand, and to debug the powerful quantum algorithms that are really going to shape the future of computing. And that really leaves us with a final thought. We just created one of the most profound phenomena in all of physics using just 2 qubits and 2 simple gates. So it really makes you wonder, if this is what's possible with such a simple blueprint, what could we build with 20 gates or 200? Unbreakable encryption? New medicines designed at the molecular level? The possibilities are really just beginning to unfold.